we're going to discuss vertex form. So all the functions we study this year are going to have some type of graphing form. With a quadratic, we call it vertex form. And what's nice about that is when it's in vertex form, we can look at the function or equation and identify the vertex right away, and then we can identify that a value right away, which is nice because that tells us where the vertex is, and then the a value helps us determine its orientation. And we'll study more of that later, but the common form here is in this box right here. Y minus k equals a times the quantity x minus h squared. Occasionally, that vertex form is also expressed this way, where that k value that's minus k right here is added to both sides of the equation, and it ends up on the right side of the function. So vertex form is the original one there printed in black, but it can also be expressed in the blue form there. The vertex is hk. Be careful. If you have the vertex, expressing it in vertex form is pretty basic, but if you have the vertex form of the equation and you're trying to identify the actual vertex, the values you see in the equation are going to appear as the opposites, just like in point-slope form. Okay, so we'll talk about that in an example. Other things we can point out here is this a value. Okay, this a value is going to dictate whether the graph opens up or down. So if a is positive, that's a is greater than 0. This graph is going to open up. If a is negative, a is less than 0, graph is going to open down. And then a also helps us dictate the stretch or compression factor of the graph, and we'll get into that in a little bit here. The idea here is to take a quadratic in standard form and then transform it, manipulate it into vertex form here. And to do so, we have to complete the square, and that's the concept we're going to focus on next here. Right? So let's not do that. So here we go. Let's get rid of this, it's not necessary. So here's a function. What do we know about the function? This is the same one previously. We knew that the vertex was 3, -4. We also knew that the y-intercept was 0, 5. The reflection point was that point I pointed out that was horizontally the same distance away from the line of symmetry with respect to the y-intercept there, but there are an infinite number of reflection points. Every point on the curve has a reflection point with the exception of the vertex. It's the same point. So we also knew that a is positive, so that means it's going to open up. It's technically a +1. And this is helpful because it just helps us understand the orientation of the graph. And the line of symmetry here is x equals 3. Okay, so what we're going to do is we're going to transform this into graphing form, or vertex form, excuse me, right? So in order to do so, we have to complete the square, right? This is a procedure. It's the same procedure every time. The next example, there's a slight tweak, but other than that, it's pretty common. So our goal is to take this standard form equation, x squared plus 4x minus 3, and express it in vertex form. Y minus k equals a times x minus h. So we need to complete the square, right? The way it works is you want to isolate the variable terms. That is the quadratic term, x squared, and the linear term, 4x. So we're going to add 3 to both sides to take that constant and push it on the left side of the equation there. And then if you remember standard form, right? Standard form is y equals ax squared plus bx plus c. So b, right here, b is the coefficient of the linear term, and we use that to complete the square, right? So what we're going to do is we're going to take b, which is right now 4, and we're going to cut it in half, right? B divided by 2, and then we're going to square it. Right? That allows us to create a perfect square trinomial, which then allows us to factor it into a perfect square, which then allows us to write it in vertex form like this. And let's go through that. So we're taking the b value, right here 4. We're going to take half of that b value and square it, then I'm going to add it to the right side of the equation, but it's an equation, so I have to balance it. I also have to add it to the left side. Right, so I'm adding 4 on the right side, I have to add 4 on the left side. I cleaned it up down here for us to see. At that stage, we're just going to clean up the left side, make it y plus 7. And then the right side here, the next step here is to take the right side of this equation and factor it, all right? So that's where we're looking for two values of positive 4. So we're looking for two factors of positive 4 that also add to positive 4, right? So two numbers that multiply to this 4 and add to this 4, okay? So that's going to be 2 and 2. And if you did this correctly, it's always going to be the same two numbers because you're creating a perfect square, right? So most of the time you're not going to write this step here, x plus 2, x plus 2, but that's the factorization of x squared plus 4x plus 4. Two numbers that multiply to 4 are 2, they also add to 4, right? So these are my factors, right? But I want to be able to express this as a perfect square. So any number or any expression times itself can also be expressed as that expression squared. So x plus 2 times x plus 2 is also the same as x plus 2 squared. That's what we wanted. That now maps it into that vertex form. There is an a value out here. It's 1, but we don't need to write the 1. But now at this point we are in vertex form. The tricky part is remembering that the h and k values are going to appear as opposites when you look at the equation, and the k value comes first. The vertex is always listed h comma k, so be careful. The 7 here is the k, that's the y coordinate of the vertex, and the 2 here is the h, that correlates to the x value of the vertex, right? So the vertex in this case, the k is negative 7, the h is negative 2. Remember, it's because the original form here is y minus k. So y minus negative 7 gives us y plus 7, and x minus negative 2 gives us x plus 2 there, okay? So the vertex here is negative 2, negative 7. We said the a was positive 1, so this graph is going to open up. So at least now we know the orientation of the graph and the direction it's going to open. And here is a graph for us to look at, right? So you got your vertex, negative 2, 7. We had a y-intercept of negative 3. We didn't identify that, but that was the constant of the function. And then, now that you know the line of symmetry exists, going right through the vertex, the distance from this line of symmetry to this y-intercept here is 2 units, which means 2 units to the left is going to give me a symmetrical point right there. Now you have 3 points on your graph. It's nice to have 5. 3 points gives you a rough sketch of the graph, but we're going to work with doing it with 5, and I'll show you a nice, easy way to get through that tomorrow. And that's our example there. We'll do one more, and then